My name is Gil Compo, and I work for the University of Colorado Cooperative Institute for Research in Environmental Sciences and the NOAA Earth System Research Laboratory Physical Sciences Division, and I lead the NOAA Series 20th Century Reanalysis. The 20th Century Reanalysis project is a global reconstruction of the weather every 6 hours back to 1871. The analysis is a jargon for the weather map, like you see every day on TV. We're doing the similar thing, but we only use surface pressure, and yet we're able to get out all the other variables, including something like the integrated water throughout the troposphere and stratosphere. We call that the precipitable water, the amount of water vapor that's above you. For Science on a Sphere, we have 3 visualizations. One is showing an example of precipitable water for the hurricane that hit Galveston, Texas. One is showing the precipitable water during the HMS Discovery mission led by Scott. And the third one is precipitable water during an El Nino in El Nino-La Nina transition from the 1918-19 period. And we chose each one for different reasons. The Galveston hurricane was fairly large scale for a hurricane, and that's probably one of the reasons that our reconstruction can capture anything. It captures a circulation, a strong circulation, and you can see how in the visualization you get an almost white circle, that it's saturated the scale that we gave. And that gives you an indication of where it goes and that it was particularly strong by having so much water vapor. The other nice thing about that particular period is that you can see the other hurricanes that are lined up. It was an active time. It was also a dramatic hurricane. It had a real effect on Texas, a lot of loss of life, damage to structures, and it was one of the early documented hurricanes. So those were some of the reasons that we wanted to present this particular visualization. For the El Nino-La Nina transition, we've been able to show that that particular pair of events was perhaps stronger than people thought previously. And that has some importance for how has El Nino been changing throughout the 20th century as we've increased greenhouse gases. So an El Nino occurs when waters in the central equatorial Pacific get warmer than normal. And that causes the storms that are normally over Indonesia to move over to the central Pacific. Because these storms are so important in global weather, then the outflow from those storms actually perturbs the jet stream and affects weather all around the globe. In this particular example, our reconstruction is suggesting that this El Nino event was stronger than we thought from the other sparse data that people have looked at before. This is also a nice event because it goes from El Nino to La Nina, which is the opposite. Instead of getting warmer in the equatorial central Pacific, it gets a lot colder. And so you have a much colder cold tongue, stronger trade winds, more storm activity here, and that also seems to have a feedback. And this particular visualization is a nice example in the water vapor, showing you how the moisture is moving back and forth as we go from El Nino to La Nina. The HMS Discovery around the area of Antarctica was interesting because it was a surprise that the reanalysis could do as well as it does with such little data. But the Discovery was on a scientific mission and was taking fairly regular barometric pressure measurements, and we use all of those to get the rest of the weather. Here, as they were going along, they got stuck in the ice unexpectedly. And so we're fortunate in a sense that they were taking data that we can use, the barometric pressure data, regularly. And so we have what becomes an early ice station. And we can use those measurements then to reconstruct the weather around Antarctica and the climate for the entire time that they're frozen in the ice in ways that they never expected. We were the first ones to try to make a 3-dimensional weather map all the way back to 1871. But some of the technology that we're using is the same technology that goes into making the weather forecast that you see every day. So when you're watching the Weather Channel or looking on the NOAA website for the weather, we're using the same kind of mathematical model, and we're using a very similar technique to blend the observations with the model, with our guess. We start with a set of 56 guesses of the three-dimensional structure of the atmosphere. And then we use the original data to draw those guesses together and move them closer to the observation. And it's that range of guesses that made us able to use very little information but use it very effectively. We only assimilate barometric pressure observations. The future of the 20th Century Reanalysis Project is really in the past, trying to go further back. And we need additional data to go further back. And that data exists. And we're now getting it out of archives like the United Kingdom's archives and US archives, getting images of those data, putting them on the web, and asking the public, citizen scientists, to help us recover that data. And we're getting a tremendous response. We have more than 20,000 users on oldweather.org who help recover the data and some who help quality control it. And then we're going to be able to use that data in subsequent versions of the 20th Century Reanalysis. These visualizations do represent new knowledge. We know something about the water vapor, the winds, the temperature in 3 dimensions in a way that we didn't before we had supercomputers and digitized observations that our forebears took. So I'd like audiences to have an appreciation of the difficulty and what the combination of the multiple sciences of thermodynamics and physics can do to help us to understand what's happening to our planet and perhaps how we're affecting it.